Welcome to today's lecture. So everything we've done up until this point has been material you will see again in Physics 130. So everything related to mechanics, conservation of energy, conservation of momentum, simple harmonic motion, waves, all of that is Physics 130 material. There's some other material that is going to be put in there, but all that you will see again next semester. We are now going to be hitting the part of the semester where we are going to be looking ahead to subjects that you'll see in Physics 230 and 231. So this is stuff that, it is related to what we've previously talked about, but it's not going to explicitly be in the exact same way we saw it before. So for example, today we're going to be looking at electric forces. So Newton's laws of motion still apply here, where technically, we can have Newton's first and second law, and that, net force equals mass times acceleration and so forth. Those things still apply in these situations. Not so much with quantum because it has its own set of rules, but with Physics 230, it's still in the realm of classical physics, even though it's electrodynamics. And some of those concepts that we introduced months ago, those are going to be coming back again and again, even as you move forward into more complicated subject matters. So by going through these materials, I hope to show you why we have spent the time we have on some of these concepts. So before we get into electric forces, let's go ahead and recap last time. So last time we introduced the transverse and longitudinal waves, so two different types of waves that you can have. With the transverse wave, the motion or the displacement of the medium is perpendicular to the direction of the wave, whereas in a longitudinal wave, they're in the same direction. We very briefly discussed sound and how sound's a longitudinal wave, travels at different speeds. And then we spent some time looking at light, which is a transverse wave. We looked at it in its reality. It's a changing electromagnetic field wave. Not that we've discussed what that means in any way, shape, or form, but we introduced this equation. The speed of light is equal to the wavelength multiplied by the frequency. And we had some equations as well for when we were going through a non-vacuum material. Now again, for air, we're going to pretend it's vacuum because it's so close to the same value. But when we start going through different materials, that speed is going to be slower for light. So today we are going to be looking into the charge model very briefly, and we're going to discuss where charge actually comes from. Both of those are going to be in this video. And then in the second video, we are going to be going over Coulomb's law. So it is just going to be two videos today. Some of the stuff in these sections, it can get pretty convoluted, so I want to make sure we spend time going over Coulomb's law and kind of how that gets used in a lot of detail, which means it's just going to be a little bit slower of how that's done. So let's talk about the charge model. So there are a lot of experiments that are detailed throughout section or chapter 22, section 1. And it has to do with glass and plastic and rubbing it with like a cloth and things like that. There's a lot of experiments that the textbook talks about. And out of that, it goes through and it discusses key aspects of the charge model with never talking about what charge is. So we're going to skip the experiments and we're just going to get to the results because there are, I think it was 13 or 14 experiments detailed on how to get it so that these rods would repel and not repel and attract each other and stuff like that. I think it's more beneficial to just go straight to what is the model? How does it work for actual charge? So that's what we are going to be doing today. So the first aspect for the charge model is that charge can be transferred between objects. So here, when we're discussing charge, it is a very particular aspect of charge that is going to be moving. We'll see that in a little bit more detail in a few minutes. But it can be transferred between objects. So with these experiments, there are 2 to more objects that are involved with touching each other. And so with physical contact, there can be a transfer of charge from one object to another object. There's only 2 types of charge. An object can be neutral, but that just means that these 2 charges, whatever they happen to be, can balance each other out. Now you might be sitting there thinking, oh, positive and negative. This section doesn't use positive and negative, it uses glass and plastic. So again, reason why we're not covering the experiments, right? But there's 2 types of charge. Like charges repel and opposite charges are going to attract each other. So this is going to help us figure out the direction of the force between our 2 objects. It is a long-range force. You do not need physical contact. So the only other long-range force we have discussed at this time is gravity. Gravity also being a long-range force where you do not need to be in contact to influence the effects of gravity. The same is true with the electric force between 2 charged objects. It is a long-range force and you do not need physical contact in order to experience the force. We'll see the equation for that in the next video. And then there are 2 types of objects, those that conduct charge and those that do not. So those that conduct charge are called conductors. Really original name. And those that do not are called insulators. And this is something that when you get into doing more electricity type things, insulators and conductors are going to be more important. How we are going to be approaching everything in this class, we are personally only going to be dealing with conductors. Insulators, they exist, they are extremely important, but we're not really going to be using them in our Physics 129 class. When you get to Physics 230, you'll see them there. But also I feel like this aspect needs a little bit of an asterisk with it. It turns out that if you have a strong enough amount of electricity, everything does eventually become a conductor. So you can have something that is normally an insulator eventually become a conductor if it's strong enough. For example, wood is an insulator. With that, you can put enough electrical current through wood, and you'll get those kind of, I think they usually sell them as like cables or something along those lines, where it's wood with like the pattern through it that's created by electricity. That is an insulator becoming a conductor. So understand the 2 types of objects. Eventually everything becomes a conductor if it's strong enough. So let's talk about charge. And in order to do that, we need to consider the atom. Now the model for the atom that is used in a majority of cases is not technically the physically accurate model of the atom. It's good enough though. So let's consider our atom. Here we have just an example of an atom. We are representing it as a nice sphere, even though in reality it's not going to be sphere shaped. In the middle, where all these little plus signs are, this is the nucleus. And the outer part of our circle, this greenish hue with the negative signs in it, that is referred to as the electron cloud. And here we see the rough size of an atom. This kind of holds true for all, not all atoms, but we like to approximate them as 10 to the negative 10 meters in diameter, or 10 angstroms. So this core portion here is the nucleus. It's the center of our atom, and it consists of protons and neutrons. And then again, this outer portion of the atom is made of electrons and is referred to as the electron cloud. Now, in the inside, these positive symbols are representing the protons inside of our nucleus. The neutrons are neutral and they are not represented when it comes to charge because the neutron itself does not have charge. The outer portion, we have the electron. The electron has a negative charge, and that is why we use the negative symbol to represent the electron. So when we are going to be considering the atom in this portion of the class, the neutron's not going to matter other than influencing how heavy the individual atom is. And very commonly, we're not going to care about how heavy an individual atom is. So the neutron's not really going to matter. It's what's happening with the protons and the electrons within an atom, and those atoms building up into the objects, that is going to be what we care about. In this object, what is happening between all of these protons and electrons? So with the charge of a proton and the charge of the electron, they have the same magnitude. They have the same numerical value. It's just the proton is positive and the electron is going to be negative. So here we have the symbol that is used for the charge of an electron or the charge of a proton. It is a lowercase e, and it is equal to 1.6 times 10 to the negative 19 coulombs, where coulombs is our SI unit. In table 22.1, we can see that the proton and electron have very different masses. However, the charge of the two of them is exactly the same. They are both 1.6 times 10 to the negative 19 coulombs. The proton is just positive and the electron is just negative. Now, something you will see throughout the textbook is that a lot of the times when discussing a proton, a positive sign is still going to be used in front of the E for the charge. This way it just confirms that yes, this is a positive number. Negative electrons, those will always have the negative sign in front of it. So even though we typically, if we just have a number written out without the positive sign, we assume positive. The textbook is going to sometimes be using positive 1.6 times 10 to the negative 19 coulombs, just to emphasize that this is positive versus this is a magnitude situation. This E value is also sometimes referred to as the fundamental unit of charge. As far as we are concerned, this is the smallest amount of charge that can exist upon an object. And the reason for that is, as far as we are concerned in our current theories for particle physics, the electron cannot be broken down into smaller components. So that means that the electron's not made up of two negative particles, it's just one object. So that means that this is the absolute smallest value you can have for a charge, because you can't have part of an electron. So that is why it's the fundamental unit of charge. Turns out you can have part of a proton, but that is way beyond where we are going in this class. So fundamentally based around the electron. To look at the charges of an object, we are going to have to consider the numbers of protons and electrons. Because again, these are the only two charged objects inside of our atom. And because these are the only two charged objects inside of our atom, they are going to determine if our atom is going to be positive or negative. And as we build up into an object, that whole object is going to have some number of protons and some number of electrons. So we need to find the difference between the two values in order to figure out, is the object positive or is the object negative? So this is the equation in order to go through and solve for the charge of an object. It's equal to the number of protons times the fundamental unit of charge minus the number of electrons times the fundamental unit of charge. So here in this equation, we are just using E for both values, and we are saying that we're going to subtract the number of electrons times the fundamental unit of charge. So we're not going to plug in negative E here, it's positive E. The negative is already being accounted for by having it pulled basically outside of the value. Or we can rewrite it as the charge of the object is going to be equal to the number of protons minus the number of electrons. That quantity is multiplied by the fundamental unit of charge. Now this is the formal equation. Sometimes instead of using a lowercase q for an object, you might see a capital Q used for the object instead. It's just going to depend. Usually what happens is if you have two different charged objects and one has a larger charge, the capital Q is used. And then the lowercase q would be used for the smaller charged object. Also, it's going to depend on your textbook. Some textbooks use capital Q instead of lowercase q across the board. So again, you guys are adults. You guys can choose your variables. So if you want to use lowercase q versus capital Q, it's your choice. But again, it's your responsibility when writing out your knowns and unknowns that you indicate what variable you're using and stick with it. So with this equation, oops, I forgot the E here. Let me just pop that in. If an object has a larger number of protons than electrons, that means that the object is going to be positive. You'll have a positive number in the parentheses. E by itself is a positive number, so this would give us a positive Q value, making our object have a positive charge. Well, you can have the opposite case as well, where you have more electrons, but in order to have a positively charged object, it must give up electrons. If we go back a couple of slides, we saw that the charge of the proton and the electron is the same. However, the mass is extremely different. The electron's to the negative 31 kilograms, whereas the proton is to the negative 27 kilograms. The difference in mass and the difference for how the nucleus is bound together versus how an electron is bound to the atom is very different. And it turns out it's going to be a lot easier for the electron to move around in comparison to either a whole nucleus or some part, a single proton being kicked from it and moving around. So in order to have a positive object, you get rid of electrons. So here we have a positive and negative ion. So again, in the middle of our object, we have our nucleus. In the case of both of our nuclei, we have 5. We have 5 protons for both. Now we need to go through and look at the number of electrons. For the one on the right, if we look at it, I don't want to use red. None of these colors are going to be easy to see, but I guess we'll just use black. We have 1, 2, 3, 4. So 5 minus 4, we're going to have positive 1. This means that on our left side, we have a positive 1 charge. On the right side, we have 1, 2, 3, 4, 5, 6. So our number of electrons is equal to 6. We're going to subtract 5 minus 6 is negative 1. So we have a negatively charged ion. So an ion is just an atom that has changed the number of electrons from neutral to positive or negative. In this very particular case, we have gone from 5 to either 4 or 6, depending on which one we're looking at. So an electron has been given up from this left atom into the right atom. So that results in charge being different for the two of them. However, there is something interesting that's happening. The total amount of charge is remaining the same. Right? If I could take this negative ion and put it back, I'm going to end up with 2 neutral atoms. So there's some rules that have to be happening in order for charge to behave accurately. And that is that charge is conserved. Charge is neither created nor destroyed. Charge can be transferred from one object to another as electrons and ions move about, but the total amount of charge remains constant. So, what this is saying is that the amount of charge is fixed. We dealt with the conservation of energy and the conservation of momentum. This is a conservation of something a little bit easier to keep track of. It's adding up to both sides add up to the same number of charge before and after there's been a change. That's all it is. The amount of charge remains the same regardless of what is happening. It's this conservation of charge that you pretty much use for, I'm trying to think, so for the first 3 to 4 weeks of 230, you do thermodynamics. When I taught 230 previously, which was not out of this textbook, so times might shift around, conservation of charge was a key aspect for, I want to say, about 5 weeks. So for about a little over a quarter of the semester, you are using the conservation of charge to accurately explain a bunch of different phenomena. Just like conservation of energy and conservation of momentum, this conservation of charge is a fundamental idea that helps explain a lot of what you're going to be looking at in terms of electricity. We're going to look at it a little bit in this class, but a lot more in 230. All right, so that's going to wrap it up for this video. Make sure to watch the next video as well, where we actually get into the forces of electricity, or charge, not electricity, charge.